Dear students, in this lab video, we conduct the experiment number 4, that is to design a passive RC lead compensating network for the given specification via the maximum phase lead angle and the frequency at which it occurs, and to obtain the frequency response, and also to determine the transfer function of the lead compensating network. Before we are going to conduct the experiment of passive RC lead compensating network, we know the objective and outcome of this experiment. Objective of this experiment is to design and analysis of lead compensator for given specification. Outcome is design and analyze and simulate the lead compensator network for given specifications. Aim: to design a passive RC lead compensating network for the given specification via the maximum phase lead angle and the frequency at which it occurs, and to obtain its frequency response. The second one is to determine experimentally the transfer function of the lead compensating network. Apparatus required: resistors R1 and R2, that's why 2 numbers, capacitor 1 number, signal generator 1 number, CRO 1 number, probes 3, connecting wires as required. Theory: if a sinusoidal input is applied to the input of the network with the help of the signal generator, steady state output as a phase lead, then the network is called the lead compensator network. The lead compensator network has a pole at S equal to 1 divided by alpha t, since alpha less than 1, t greater than 0, and a 0 at S equal to 1 by t. The lead compensator improves the steady state behavior of the system while nearly preserving its transient response. Where the lead compensator network used, whenever we need the low steady state error is required, we use the lead compensator network. Now you see the circuit diagram. Input Vn is given to the lead compensator network with the help of the signal generator. The output is taken from the CRO. The R1 and C resistance R1 and capacitance C is connected in parallel. The parallel combination is in series with the resistance R2. After designing, we get the value R1 equal to 4.7 kilo ohm, R2 equal to 1 kilo ohm, C is equal to 33 kilo farad. Now, how to derive the transfer function experimentally? The step 1, apply Laplace transform to the lead compensating network and simplifying the parallel combination of R1 and C. So, therefore, R1 multiplied by 1 by Cs divided by R1 plus 1 by Cs equal to R1 divided by R1 Cs plus 1. The second step is analysis applying KVL, that is Kirchhoff's voltage law, to the lead network. Then after taking Laplace transform, the input voltage VI of S equal to Z1 plus Z2 as it is I of S. In this equation, where I of S is the current in the lead network, Z1 equal to R1 parallel with C, Z2 equal to R2. Therefore, the output voltage after taking Laplace transform V0 of S equal to Z2 as it is I of S. The transfer function is output divided by input. Therefore, V0 of S is divided by V of S equal to Z2 divided by Z1 plus Z2. After simplifying this transfer function equation, we are getting the general transfer function is GC of S equal to S plus 1 by T divided by S plus 1 by alpha T, since alpha less than 1, T greater than 0. In this formula, where alpha equal to R2 divided by R1 plus R2, the time constant T is equal to R1C, this is equation 1. The corner frequencies are 1 by T and 1 by alpha T, this is equation number 2. Now we find the maximum phase lead angle, pi m equal to sine inverse 1 minus alpha divided by 1 plus alpha. This is equation number 3. Omega m is the frequency at which pi m occurs. Design: the sine pi m equal to 1 minus alpha divided by 1 plus alpha. Alpha equal to R2 divided by R1 plus R2. Time constant T equal to R1 into C. The frequency, maximum frequency omega m equal to 1 divided by T into root alpha. The next pole 0 configuration. In the pole 0 configuration, the lead compensating network and the pole, that is S equal to 1 by alpha T. Since alpha less than 1, T greater than 0, the 0 is S equal to 1 by T. You see, this is the indication of a pole. This is the 0 is the indication of 0. The cross mark is indication of the pole. So here the pole is minus 1 divided by alpha T. The pole is minus 1 by T, because this is the positive side, this is the negative side, that's why we can mentioning the negative. So this is the pole 0 configuration of the lead network. The next, how to calculate the corner frequency. We know omega 1 equal to 1 by T. The omega 1 is equal to 2 pi f1. Therefore, the f1 equal to omega 1 divided by 2 pi T. But T is equal to R1 into C. So, therefore, the F1 equal to omega 1 divided by 2 pi R1C is the first frequency. Then second frequency omega 2 equal to 1 divided by alpha T. Omega 2 equal to 2 pi F2. Therefore, F2 equal to omega 2 divided by 2 pi alpha T, where T equal to R1C. Therefore, F2 equal to omega 2 divided by 2 pi alpha R1C. Then omega m equal to root of the multiplication of omega 1 and omega 2. You can substitute the value instead of omega 1 and omega 2. Finally, we are getting omega m equal to 1 divided by T into root alpha. Therefore, the omega m is nothing but 2 pi fm. Therefore, the fm equal to omega m divided by 2 pi root alpha into T. T is nothing but R1C. Therefore, Fm equal to omega m divided by 2 pi root alpha R1C. So, the corner frequencies omega 1, omega 2 and omega m, that is F1, F2, F1. Now, we draw the Bode plot for the lead compensating network. You see, first you can find the magnitude and the phase. So, the first half, okay, this is the first half, this is the magnitude in decibel. From this length, you can find the magnitude of the lead compensating network. The second part is to find the phase in phase angle, that is the degree. So, x-axis is frequency, y-axis is one is phase, another one is magnitude. We can get this graph. So, you see, this graph represents the Lissajous figure of RC lead compensator network, which is getting from a CRO. Okay. You see, this is the A, this is the B. So, this is known as the Lissajous figure of RC lead network. Okay, from this line, how can we calculate the phase angle pi sine inverse of A by P? The A and then B is calculated from the CRO value. Okay. Now the procedure. First we derive the transfer function and design the lead compensator network, and then we can calculate the alpha, time constant T, pi m, F1, F2, corner frequency F1, F2, Fm, everything. Now switch on the main supply, apply the sinusoidal input to the lead network with the help of the signal generator. The frequency of the signal is varied in step by step. At each step, we note down the corresponding magnitude of the output voltage and phase angle using CRO. Now draw the frequency response of the lead network and find the transfer function and then compare with the design. Students, now I play the video. From the video, you clearly understood how we connect the circuit as per the circuit diagram, RC lead compensating network, and then how to conduct the RC lead compensating network. Dear student, Now I explain the RC lead compensating network. Aim is to design the passive RC lead compensating network and to obtain its frequency response. Also to determine experimentally its transfer function. Apparatus required: one number signal generator, CRO 1 number, probes 3 numbers, then resistance decayed box 2 numbers, capacitance decayed box 1 number, and then connecting wires. Now R1 I set the value, that is the 5.6 kilo ohm. R2 is 2.7 kilo ohm, and then capacitance equal to 0.1 microfarad. Connections: the incoming terminal of the R1 is connected to the incoming terminal of the capacitance. The outgoing terminal of the R1 is connected to the outgoing terminal of the capacitance. So the R1 and the C both are connected in parallel. Then the parallel circuit connected in series with R2. So therefore the outgoing, that means terminal of the capacitance, that means is connected to the incoming terminal of the R2, and then the outgoing terminal of the R2 I connected it to, one is signal generator, another one is input probe, another one is output probe. So 3, that means negative terminal I connected it to signal generator, input probe, output probe, and then the signal generator and then the input probe, the incoming waveform, that is the positive terminal I connected to the incoming terminal of the R1. In the output probe, incoming terminal I connected to the incoming terminal of the R2. This is the connection procedure. By using, that means the waveform button I select the sine wave. Using the range button I select the 1 kilohertz. For what purpose I support 1 kilohertz? I have to set the peak to peak input voltage 3 volt by using the amplitude knob, and then these buttons, and then I have to set the peak to, see here 1, 2, 3, 4, 5 divisions multiplied by 0.5 volt, we are getting 3 volt input. So output also I put in the channel mode 2, then this is also 6 volts only output. After that you can vary the frequency. You vary the frequency, some ranges, you can see the waveform. So this is the output waveform. So in the output waveform you can see 1, 2, 3, 4, 5, 6. 6 into that 0.5, that is the 3 volt output voltage. Input also 3 voltage. Input voltage should be constant for all the values. And then time per division, this is the x-axis time. So therefore you can see the positive to negative. This is the positive. So therefore 1.2 multiplied by, that means here and all 5, that means milliseconds. So 1.2 multiplied by 5 milliseconds, you are getting the time. So frequency, output frequency is equal to 1 by that time period only. You note down in the tabular column, and then you can calculate the gain formula 20 log output voltage divided by input voltage. Again you can vary the frequency, some value. Now I set the 3.075 kilohertz. You see the waveform and all. So you can change it. The waveform time mode and all, you can change it and all. So now you can visible only. You see now and all 1, 2, 1, 2, 3, 3.3 multiplied by 1 only. Up 3.3 output voltage. And then the frequency is, that is the here and all 0.5. That means millisecond multiplied by, the division is negative. This is 1, 2 and then 3, 3.2. You can get the time converted to frequency. So like that you can take the reading from 1 hertz to 3 megahertz. Then you can take the 10 to 15 sets of 15 readings and then note down in the tabular column. In the tabular column consists of frequency, output voltage and then gain. Input voltage should be constant 3 volts. Students, from the video play you clearly understand the conduction of RC lead compensating network. Now you can frequency from the signal generator, output voltage from CRO, and then the phase angle from the laser figure you can calculate it, and then the gain how to calculate it, 20 log V0 divided by Vi. By using this formula you can calculate the gain. All the four values are tabulated. Now you can draw the graph. This is the expected model graph. So the x-axis is frequency, y-axis magnitude in decibel. This half is the magnitude, this half is the phase angle. Okay, so first this is the 0 decibel, then you can increasing the value like this. This is the magnitude shape. So this is the phase angle shape. This is the maximum angle pi m. At that time, what is the omega m equal to 1 divided by root alpha t, we already know. So in this case, this is 1 by t, corner frequency 1 by t, another one frequency 1 divided by alpha t. This is the f1, this is the f2, this is the maximum frequency fm. This is the expected graph. Okay, now this is the actual graph. So x-axis frequency, y-axis here phase and then magnitude, and then you can draw the curve. The shape of the curve is similar to expected graph only. Now the result. Thus, the passive RC lead compensating network is designed for the given specification via the maximum phase lead angle and the frequency at which it occurs, and the frequency response is obtained. The transfer function of the lead compensating networks is determined experimentally. This is the Viva voice questions. First you know the phase lead. What is the definition of phase lead? Phase lead is nothing but the positive phase angle is called the phase lead angle. There are two types of compensation is there. One is series compensation or cascade compensation. Another one feedback compensation or parallel compensation. Then three types of compensators: lag compensator, lead compensator, lag lead compensator. First, what is the meaning of compensator? A device inserted to the system for the purpose of satisfying the specification is known as the compensator. The next, what is mean by compensation? The compensation is nothing but the design procedure in which the system behavior is alerted to meet the desired specification by introducing additional devices called compensator. What is the use of lead compensator? The first one is speed up the transient response. Second one is increases the margin of the stability of the system. Third one is increases the system error constant to the limited extent. Then why the compensation is necessary in the feedback control system? The first one is when the system is absolutely unstable, then the compensation is required to stabilize the system and also to meet the desired performance. Second one is when the system is stable, the compensation is provided to obtain the desired performance. Dear students, I hope that in this lab video you clearly understood how to conduct the passive RC lead compensating network. Thank you students for watching this video.